So another example here. Oh, I've done a lot for this class. Whee! This is a pressure vessel stress example. I think I added some stuff to this. Oh, and I think I meant to change this to 1,000 kilonewtons for the loads. Yes, I did. So I have a storage tank pressurized to 150 kilopascals gauge. And it contains water at a height of 15 meters, and the outside diameter of the tank is 6 meters, and the wall thickness is 12 millimeters. Horizontal force of 10 kilonewtons, which I am saying I've changed to 1,000 kilonewtons, which seems like a whole lot. And that's a horizontal force, and a vertical force downward of 1,000 kilonewtons. That's a whole lot too. Are applied to the top of the tank. We're going to determine the absolute maximum shear stress at the location of maximum stress on the outer surface of the tank at its base. Neglect the weight of the tank material. The density of water, according to this, is 9.81 kilonewtons per meter cubed. So, like, did I change this thing in here? I did not. I need to change my notes then to be 1,000 and 1,000. I think I did it because the other values weren't like proportional, so I wanted to get some kind of meaningful proportional values. But what am I trying to find anyway? I'm trying to find the maximum stress. The maximum shear stress, absolute maximum shear stress. All right, great. So let's switch over to document camera. So exit out of you, come back over to here. Here is the problem, and I have blank paper somewhere right here. So blank paper. Okay. And okay. I didn't eat lunch again. I forgot. It's like 4 o'clock. I'm hungry. Just now hitting me. All right. So I don't know if I need to do the free body diagrams on this. I'm looking at my own work right here. And I'm trying to decide. I have 2 pages of this, and I can't decide which one is supposed to be correct. All right, so let's go on the loads side of things. All right, so we'll go loads, and we got a pressure at the top is 150 kilopascals. All right, so 150 kilopascals at the top. A storage tank pressurized too, so that's a 150 is right here at the top, and then but it then also has this high right there. It's 6 meters high. So if you want to find the pressure, you take the pressure on the gauge, right? So if we want, we'll take, it's called that PO. That's right up there, and you take the density of water, or the weight density of water, and multiply it by the height. So we start out with 150 kilopascals. So it's 150 E3. So now we got them into pascals, aka Newton meters. And we want to add to it 9.81 E3. Is that correct? Yep. Times our 15 meters. I said 6 meters actually. That was that's the diameter. 6. All right, so that's 15. Right, so that's kilonewtons. So just with the 3, that's newtons per cubic meter times meter. So now I have, that's going to be newtons per square. Okay, so now I'm going to get out the right units right there, and I get and then I divide it by 1,000 again. So I have 297.2 kilopascals. I know it's kind of confusing right there. I could have left off that right there, but I decided I just want to be kind of careful that I didn't like get them mix up some of the units in there. Okay, and let's see. Other things that I'm going to want to know in terms of loads, I could do a free body diagram right onto the thing. And it's got this and this, and here's a reaction, and there's going to be a moment about this thing at the bottom. This is going clockwise, so this should be counterclockwise. That should be moment, so the sum of the moments is equal to 0, blah, blah, blah. And so the moment that's going to be onto this thing is, this is I'll label it as 1,000, right there. 1,000 kilonewtons, 1,000 kilonewtons, and 1,000 kilonewtons happening right there. Here's the reaction in the y direction. Here's the reaction in the x direction. So this one taken about, I guess it's about the z. This moment is going to be minus 1 million newtons times this height, which they said was 15, right? I guess the height of this thing is also like, it's filled right up. It's filled to the brim. So that's 15. So you could guess that the M reaction is going to be 15 million Newton meters. Whee! That's a lot. Okay, there's some loads. I need some geometry, actually. I need the area of this thing. All right, so that's going to be pi over 4 dO squared minus DI squared, right? And I'm not going to bother writing all that out, but it is 6 meters in diameter, but the wall thickness, and you're going to have to subtract out 2 of them, is 12 millimeters, right? So we're subtracting out 12 millimeters from this guy right here. So it ends up being 0.2257 meters squared. And I is going to be equal to pi over 64. We noticed that, okay, and that's dO fourthed minus DI fourthed. Once again, plug those numbers in, you get 1.012 meters fourthed. We don't need J because there's no torque on this thing. This is going to be all normal stresses. Okay, so we're ready for stress, I think. Yep. There was loads up here. We could actually say that this is geometry. And sometimes, some semesters, I'm really good about remembering to do this over and over again. Say, geometry, loads, stress combined, right, each time. So maybe I'll try to remember to do that this semester. Maybe. Axial. It's just going to be Fy over A. So that's 1 million. 1 million divided by 0.2257. We end up with very boring 4.430 megapascals. But this force is coming down, that 1,000 kilonewtons is coming down. So that's compression. That's down here at the bottom. We have bending. MC over I, right? And we might want to pick out the worst case. Well, we know it's going to be bending and going to be tension and compression, depending on which side that you talk on. On this side, it's going to be tension. On this side, it's going to be compression, right? And hopefully that you can follow along with that. And we're at 15 million. And C is going to be 6 meters divided by 2. And I is going to be that 1.012. So you can kind of see that we get 44.48 megapascals. And this is T and C, depending on which point that you want to point out. But that's going to combine with here. It's going to make it that could make it. All right, but let's continue on. We have to decide, by the way, some of the geometry we might want to have picked up on somewhere. We said the radius was equal to 3 meters, and the thickness was equal to 0.012, right? So the thickness divided by r ends up being 0.004. Therefore, this is thin. And so now for the longitudinal, I'll just write this L right there, it's supposed to be an L, is going to be P DI divided by 4T. Does that DI really matter? I went ahead and used 6 meters. But let me see, I'm going to calculate this out. So the pressure on here needs to be, I want megapascals, and I was given kilopascals. So this is 0.150 is the pressure in megapascals, because they gave us in kilopascals, but I'm going to stick with these other units right up there. And this is going to be 6 minus 2 times 0.012, right? 4 and divided by 0.012. So what does that end up equaling? I don't think it's a lot. 6 and 0.012 times 2 minus, we get 5.976. So this is 5.976 times 0.15, boom, divided by 4 and divided by 0.012, divided again, boom, and I get 18.68 megapascals, and that's going to be in tension, because that's that thing trying to rip the thing up, right? And one thing I want to make sure that we're using 0.15 because that's the pressure that's causing longitudinal. It's not this pressure up here. That pressure is going to cause hoop locally at the base of this tank, right? Got to be careful right there. That's a little weird. And if I just use the outside diameter right here instead, I get 18.75. So there's not that much. It's like a 0.2% error or thereabouts, something like that. For tangential is my P DI. This is the average 2T, right? But got to be careful here. It's a 0.2972 times my, what did I say? I forgot to put it down. 6 and 0.012 times minus, here's our 5.976 divided by 2 divided by 0.012, and so 0.012 divided 2 divided 0.2972 times, and I get 74.00 megapascals, and that's in tension right there, right? So looking at a small element at the base of this pressure vessel, I think so the worst thing is going to happen is we're going to have 74 in tension and 44 in tension, and then this in compression. So it makes sense that we're going to add these two together. We're going to take the tension side to the We're going to take the tension side of this and the tension side of that and subtract out the compression of that, right? Because we could have either used the tension or compression, but this is going to be significant enough that it's going to be the worst like magnitude of stresses, which is really what we want to have. So if you're looking at a little QB that's taking place right there on the wall, we're going to say it's over on this wall over there. We have a compression coming down there, we have tension, and we have tension. Right? That's in the Y direction. In this direction, we have hoop. Right, and it's on the outside, so there's nothing going on in this direction. right? There is no here. So this is the T. This is let's see, bend. This is axial, and this is longitudinal, right there, the L. So the sigma y is going to be, what is sigma y? Sigma y is going to be 44.48 plus 18.68 minus 4.430. So we end up getting 44.48, 18.68, and subtract out 4.43, and I get, where are you at? 58.73 megapascals tension, and we already had what the what this one was going to be, right? So when looking at a, let's say that this is the, I don't know which way to call this right here, right? So this is, we're going to be looking at this face, and this is the Z direction, that's the Y. So that's the Z, and that's the Y. And so this is 74, and this is 58.73. Now, the thing is, on a Mohr circle, how would we plot this out? It's going to be this point and that point, right? There's no shear going on. So right here is how we plot it out. And there's a 0 is sigma 3, sigma 2, and sigma 1. This is equal to sigma 1. This is equal to sigma 2. Sigma 3 is this. Right there is the 3D Mohr circle, and the tau abs max is sigma 1 minus sigma 3 divided by 2. Or in this case, it's just going to be 74 divided by 2, right? Because sigma 3 is 0. 74 divided by 2 is 37. I needed a calculator for that. So I think the way that the question was asked, determine the absolute maximum shear stress at the location of maximum stress on the outer surface of the tank. Okay, whatever. Tau abs max is equal to 37 megapascals. The end. It wasn't terribly difficult.